Okay, so the first thing that I want you guys to realize is that what we're doing here is we're moving from depictions of motion on graphs to depictions of motion under certain conditions on graphs to mathematical representation of those depictions to being able to use those mathematical representations to make measurements and predictions. So we are today going to start the process of moving from the graphs that we've been using, which are super useful, critical. We're going to move from that to being able to make calculations. So the example that I gave you all on Monday when I was talking about, or maybe it was last week, when I was talking about if you have a car crash and you're an investigator and you need to figure out how fast that car was going right at the moment of the collision, we can figure that stuff out. We need just to know a few things, and then we can make a prediction about that car's velocity at the moment of the collision. So the skills that we're going to look at has to do with position, velocity, and acceleration graphs under the constraint of constant acceleration. That is going to include when acceleration is 0, though we're not going to hit that until Thursday. And then we're going to start thinking about equations, and we'll finish that work up on Thursday as well. So this is going to be broken into 2 parts. The first part, I have this little illustration for you. So this is oops, hang on. All right. So this is a nice little app that basically what this does is it allows you to shoot a cannonball out of a cannon, and you can raise up the height, and you can change the angle, and you can change how fast it goes, and if you launch it, then it'll go a certain distance, and this has happened in the last class too. That's just a coincidence. I didn't know how far it was going to go. It just happened to go that far. But what's interesting about this is we've got some common sense about these things. So if I want it to go farther, for example, I know I need to do something different. Maybe I could raise it up. Maybe if I raise it up, it'll go farther, and it does. Maybe if I give it a little bit more speed, it'll go farther, and it does. And it went a little too far there, so maybe what if I play around with the angle? Maybe I can make it go shorter if I change the angle, and yeah, it doesn't. We know, right? You all have been doing this kind of physics for most of your lives. Did you see what just happened? Did you see that? Those two just parted like this. They knew where that Nerf ball was going. They didn't catch it because since I threw it, they assumed that it had poison or spikes or something horrible like that on it. But you could have caught it easily. That would have been an easy catch. But you didn't. Instead, you just moved, right? And that's because you knew what path this was going to follow. You didn't need to see it come right next to your head to know, oh, it's going to potentially hit me. You saw it from right here, and you knew, oh, well, by the time it gets halfway, you knew exactly where that was going to go. There's a predictability to this kind of motion, and we're going to take advantage of that predictability. It happens in this case in 2 dimensions at the same time. This cannon is firing the cannonball to the right and also up or down at the same time. And so that's a little bit of complication that we're not going to get into until next week. But the basic mathematics behind that motion is pretty straightforward. It starts with recognizing that if you have constant acceleration, there's an equation that we already know that is going to describe the acceleration versus time. It's going to be a horizontal line. So the shape of an acceleration versus time graph is going to be a horizontal line in general in xy coordinate space. If we talk about a horizontal line, it looks like this. Y is equal to a constant. Specifically for this graph, the y-axis is acceleration. The x-axis is time, but our x-axis variable doesn't show up in the equation for a horizontal line. So this graph right here is telling us that the acceleration is going to be a constant value no matter what time it is, no matter how much time has gone by since we started making observations, the acceleration is always going to be the same, perfectly horizontal line. And that means that the slope of the resulting velocity versus time graph is going to be constant, because we figured out that on a velocity versus time graph, the slope is the acceleration. Those two quantities have the same value. If you calculate the slope at any point on a velocity versus time graph, you are calculating the change in velocity divided by the change in time, rise over run. That change in velocity over change in time is our definition of acceleration. If you have a constant acceleration, then you're going to have a velocity versus time graph with a constant slope. It might be 0, by the way, but not in this example. So that means that your velocity versus time graph is going to be a line. Usually it's diagonal. If there's no, if there's non-zero acceleration, then our slope is going to be non-zero, and that means that our line is going to follow the familiar y equals mx plus b form. Okay, that's on an xy graph. This graph has a y-axis that's equal to velocity and an x-axis that's equal to time. So our velocity is going to be equal to the slope of this line is equal to the acceleration. So acceleration times our x-axis variable, which is time, plus the y-intercept. And the y-intercept is a velocity. It's the velocity that this object had right at the start of the time period that we're interested in. We often call that v0 for initial velocity, velocity at time 0. So our velocity versus time graph is going to be a diagonal line if we have a non-zero slope. Okay? And the slope will be non-zero if we have a non-zero acceleration. Things look different with zero acceleration, but we'll look at that on Thursday. And that's going to allow us to predict what our position versus time graph looks like, because we know that the slope of a position versus time graph is velocity. The problem is our velocity is constantly changing here, which means our slope is constantly changing. The slope of this line is getting steeper and steeper and steeper. And there's math that we can do to work this out, but it turns out that really all we need to know is that this shape will be a parabolic curve, or part of a parabolic curve. And that's if there's non-zero acceleration. Then we'll get a parabolic curve, and the equation for a parabolic curve in xy coordinate space, does anybody remember? It's a tricky one. I mean, it's not super tricky. You've done this, but you probably have forgotten.
X squared?
Yeah, it's the x squared thing, yeah. So it's, yeah, that's great. So it's y equals some parameter times the x variable squared plus some other parameter times the x variable plus some third parameter. So it's complicated. This, by the way, is where we get the quadratic equation, right? That's the a and the b and the c from the quadratic equation. It all sort of works out. If we set this equal to 0, then we can solve this using the quadratic formula. And this, so it's not as easy to relate all of these parameters to this graph, because we can't just say like, well, this is going to be the slope, because the slope depends on, like, it's changing. So there's not just one thing that's the slope. So there's some sort of combinatory aspect to this equation. But we can figure out mathematically, and I'm not going to ask you to do this, but it's not super difficult using just a little bit of calculus to show that this is going to reflect an equation that shows position, which is our x variable along the y-axis, thank you physics, that's going to be equal to 1/2 of the acceleration, so 1/2 of the acceleration, so it's related to the acceleration, times our x variable squared, plus whatever our initial velocity is, times our x variable, plus the initial position. So this is a complicated one. I wouldn't expect you to be able to figure this one out. This one, with a little bit of geometry, you could actually figure out on your own. And this one, most of you could figure out on your own, even without geometry. Like this one is pretty obvious. Acceleration is constant, you get a horizontal line. If acceleration is slope, this is not too difficult to tease out. If velocity is slope on a position graph, you need calculus to get to here, okay? But it's doable. So these, not so much this one, although it's critical that acceleration be constant for the other equations to work. But these two equations end up forming kind of the basis for the work that we're going to do as we start making measurements and predictions. So before we can really use the equations, we have to figure out what all our different variables are going to mean. And so what we'll do is we're going to use the variables the way they're defined in the AP Physics equation sheet. So those of you in AP Physics will get this or something really similar to it when you take the AP test. And the variables that they use are slightly different than the variables in the book. The variables in the book are clumsy, so you can use them if you want, but I wouldn't. Other people use slightly different variables. Being able to be fluent with this is going to be pretty important. Depending on where you look, you're gonna see different variables. It's not by choice, it's just that's unfortunately the reality. So when we talk about time, there's really kind of three things that we need to think about. One is, when do we start caring about something? And a lot of times, things are happening in a real life scenario or in a problem, and we don't care for a little bit. Like when you've got your carts on the track, there may be a time during which you're recording a video and you're holding onto the cart, and then you let go. That part where you're holding onto the cart shows up on the video, but you don't really care about it because there's no way you can really make a prediction about what's going to happen. Once you let go, you do care. That time we call the initial time, and the variable we're going to use for that is t0, and the units for that are typically in seconds. We'll bounce around with units a little bit. In general, I'm going to try to stick with seconds for time, but in the book, they may use minutes or hours or years or whatever, and outside of the book, who knows what time units they're going to use. And then some time goes by, and sometimes in a given situation, we have kind of two defined boundaries. We have some initial time and some final time. Sometimes we think about, well, there's an initial time, and then what's happening here, and what's happening here, and what's happening here, and each of those heres represent different times on like a video or a stopwatch or like a clock. And so the variable t refers to whatever like some later time is. And sometimes we have multiple later times. So sometimes we might be like t1 and t2 and t3. Sometimes we just have one later time and it's t. Sometimes we're just wondering about what's happening right now, and now what's happening, and now what's happening, and that would be t as well. And the units for that, of course, is going to be seconds. A lot of times, what we're really concerned about is not when did something happen, but what happened over a period of time. Okay, so that is the amount of time that goes by. We use delta t. Delta is the universal science and math symbol for change. So delta t means change in time. Mathematically, that's going to be final minus initial time. That's going to be measured in seconds as well. And just in case things weren't tricky enough, a lot of times sometimes our initial time is time 0, which means our change in time is some final time or some current time minus 0, which is the same as the final time. And this is going to get confusing sometimes, largely because physicists sometimes just use this as a shorthand for delta t. And that's because they know when they mean change in time and they know when they mean in instant in time. If I time something on a stopwatch and I want to know how far it's gone, I don't care what the stopwatch says at the end of the motion. I care how long the motion is occurring. So if you start your watch right now, if you want to know how far I go, if you start your watch right now, time 0, 1, 2, 3, 4, 5, 6, I was moving for about a second and a half. The delta t is what matters there. I started moving at t equals 4. I stopped moving at t equals 5.5. But those times aren't meaningful. What matters is that I was moving at a roughly constant velocity for about a second and a half. Much of the work that we're going to be doing over the next few weeks is going to involve this. We're going to be using t as a shorthand for delta t, because what we really care about is the length of time over which motion was occurring. And you'll see lots of examples of that. We'll get lots of chances to sort of play around with it. And then we have an initial position, and I showed you what that looks like already. That's going to be a variable like x with a 0 by it. And typically, we're going to measure that in meters. Again, sometimes it'll be feet, sometimes it'll be miles, but I'll try to stick to meters. But it might be a y variable or a z, or sometimes you or somebody else might say it's the p axis, and then your variable is going to be p. There is no law that says x has to be our position variable. There's no law that says our horizontal axis has to be x. There's no law that says our horizontal-ish axis has to be x. What you'll find is that typically, if we know motion is horizontal or close to horizontal, we call it x. We call that axis x. If we know nothing about the direction of motion, then we call it x, and we sort of picture it as horizontal or horizontal-ish. If we know that it's vertical or mostly vertical, then we call it y. But none of that is locked in stone. So we'll use y when it's meaningful. We'll use x when it's meaningful. There are going to be times, and you may discover this in the motion analysis today, that if you put those axes up and you start rotating them, you may accidentally switch your axes. I had some students, I think it was during the first period class, but some of you might have found this too, that they just inadvertently rotated their axes so that the y-axis was along the ramp. Did you do this? And the x-axis was perpendicular, and that's fine. There's no law that says you got to make that horizontal-ish axis the x-axis. So the x or y is a user-defined term. Okay? And then our final position is going to be just regular x or y. And again, this might mean where you are at any given time, or it might mean where you are at the end of the time period in interest. It depends on the context. And that's going to be measured in meters as well. And we already talked about the definition of displacement, but just to make it abundantly clear, displacement is always going to be whatever your final position is minus your initial position. And then velocity is a little bit more complicated because we can have velocity along multiple dimensions at the same time. And we'll talk more about this next week. For now, just recognize that anytime you use a velocity symbol and you're talking about an object's one-dimensional motion along a line, you have to identify which axis you're talking about. We're only thinking about one-dimensional motion right now, which is typically either going to be x or y. And so we're either going to have an initial x velocity or an initial y velocity. Next week, we're gonna have both. And there's also the matter of like objects having sort of an overall velocity that's neither along one-dimensional axis or along another one-dimensional axis, but is instead at an angle to both, and we'll need to be able to talk about that as well. This is going to be measured in meters per second, and then our final velocity, as most of you have probably predicted, is just going to be Vx or Vy or Vz or whatever we're looking at. That'll also be in meters per second. And then we can think about change in velocity the same way that we thought about displacement. Change in velocity is just going to be whatever our final velocity is minus whatever our initial velocity was. And that's going to be per axis generally. We're going to look at one-dimensional motion, and when we get into two-dimensional motion, you'll see how we do it. There's some mathematical trickery that is going to allow us to look at motion like that projectile that I showed you in terms of horizontal only and vertical only. It's a crazy physics trick, and it works every time. Okay, and then the last term is acceleration. We do need to think about acceleration in more than one dimension, so we need to identify our acceleration dimension as either x or y or whatever else, but the problems we're going to be dealing with in general, at least to start with, are going to have constant acceleration, which means our acceleration variable doesn't have an initial and a final. It's always the same. And our units are meters per second per second. Acceleration measures the rate of change in velocity. Change in velocity is going to have units of meters per second. The rate at which that changes is going to be an amount of velocity, of meters per second. If you do the unit analysis mathematically, that ends up being meters per second squared. So these are the variables that we're going to use. You may see different ones referenced, like sometimes people use xi and xf for this. The book puts them in parentheses. The book drives me crazy. It's got like x0 in parentheses, and then, I don't know, it's just got all this stuff. The V's have all these parentheses. It's terrible. But the AP Physics uses this notation, so that's what I'm going to try to standardize on. And if you ever see me using something different, just ask, like, what do you mean by that? What's VI? Well, that's initial velocity, and I'll try my best to stick to this. Okay. Any questions about this? All right. So we're going to take that, and we're going to think about those graphs that we just saw, along with some other stuff. And we're going to build some equations. And these equations are going to form the foundation for the predictions that we make. Two of them are obvious right off the bat. One of them comes from our equation for a parabola that shows final position as a function of time. And that one is going to look like this. X is going to be equal to, and I want to put it in the right order. Okay, so it's initial position plus initial velocity times time plus 1/2 times the acceleration times time squared. Okay? So this is an equation that in general talks about position as a function of time. But there's 5 variables in here. If you can measure any 4 of them, you can find the 5th. If you measure all of these variables, you could find an object's final position. But if you measure its displacement, initial and final position, and you know how long it's been moving, and you know its acceleration, you can calculate how fast it must have been going at the start. Or you can find how long it's been moving. You might need to use the quadratic formula for that. So that's one of our equations. Another one of our equations is also obvious from the graphs that we looked at. The final velocity of an object in any dimension is going to be equal to its initial velocity in that dimension plus its acceleration times the amount of time that went by. This is our equation, our parabolic curve that you get when you graph position as a function of time when you have constant acceleration. This is the diagonal line that you get when you graph velocity as a function of time under the conditions of constant acceleration. And then there's 2 more equations. One of them is you get by using the other three. And it's pretty useful, and you do not have to know how to derive it. It looks complicated, but it's super handy, and it's this. If you square the final velocity of an object, that's going to be equal to its initial velocity squared plus 2 times its acceleration times the displacement. Final position minus initial position is displacement. So displacement times acceleration times 2 plus the initial velocity squared will give us the final velocity squared. And that's like, why would you ever use that? That's such a weird, cumbersome equation with like squareds, and you'd have to do square roots and all sorts of crazy things. But the nice thing about this one, we don't have to know time at all. We've got variables in there, but we don't have time. And that can be super handy if you go back to like the car crash problem. Like if you think about a car slamming on the brakes, skidding to a stop, you know its final velocity is 0 because it's stopped. You know its displacement because you can measure how long the skid track is. And if you can figure out in general how quickly that particular car with that particular kind of tire on that particular road surface will slow down, you know its acceleration. And that seems like a crazy thing to know. Like how could you possibly figure that out? But you know who does that, and you know who knows? Is the insurance companies. They have big tables, and those tables have all that information. If you go to an insurance company and you say, I have a 1996 Ford Explorer with 3-year-old Firestone tires, how long is it gonna, like what's my acceleration if I'm skidding sideways on concrete? And they'll be able to tell you. Like it's that, they have it that dialed in. They've made all those measurements. The last equation we actually get from our definitions, and it's used to build this one along with the other two. The last equation relates average velocity, which we defined as displacement divided by the amount of time that goes by, to the mathematical average of 2 velocities. And if you look back, so hold tight, I'm gonna come right back to this, but if you look back at our velocity versus time graph right here, under the conditions of constant acceleration, the average velocity over this time period is gonna be the midpoint of the y-axis of this line, which means if we add the initial and the final velocity and divide them by 2, we'll get the average velocity. That won't work if acceleration isn't constant. But if it is constant, then average velocity will be equal to initial velocity, oops, wrote that wrong, initial velocity plus final velocity divided by 2. And if you take this equation, solve it for time, and plug it into this equation, you get this equation. So that's where this one comes from. You don't need to be able to do those derivations. This 4th equation up here isn't essential. You won't necessarily need to use it. You can get here by using these in 2 steps. But I use this one sometimes, I find it handy. And the key piece of information that you need to know in order to be able to use these equations is that they only apply when acceleration is constant. So these are only meaningful when acceleration is constant. And this is the source of a lot of trickery, especially on the AP exam, because you can use these equations even when acceleration isn't constant. They just will give you garbage. If I tell you that your acceleration is all over the map, and then I tell you that well, I could give you something like this. I could say, what's the average? It starts at 0 meters per second, and it ends at 10 meters per second. What's the average velocity? You might be like, well, it's 5, right? Not necessarily true. If acceleration isn't constant, that's not true. If we have constant acceleration, then our velocity graph is going to look like this. And that means the average velocity is halfway in between the slowest and fastest speeds over that time period. If we have non-constant acceleration, then for all we know, the velocity looks like this. And that means the average velocity is way closer to the final velocity than it was to the initial velocity. So these equations will give you numbers, but they may not be meaningful unless acceleration is constant. And the only other thing that I want to point out here is that in all of these equations, t refers to the change in time. So a lot of times our initial time for whatever we're talking about is 0, and that's great. If you know that time 0 is when you start being interested, when constant acceleration begins, great. Sometimes we don't know that. Some of you were on the motion cart video analysis. Hang on, let's see if I can find something right. But some of you were seeing graphs that looked like this. You made graphs. Did anybody see something that looked like this? Did anybody see that? Anybody do that? This is what you would get if you let your cart bounce off the end. So it rolls down the cart and bounces back and then back down to the bottom and then back up and then back down to the bottom, back up and back down to the bottom. It turns out that there's constant acceleration during all of these time periods. So you could conceivably evaluate this time period right here. Find the acceleration, the initial velocity, all sorts of stuff. This isn't time 0. This is our initial time of, I don't know what, like 0.8 seconds. And our final time is maybe 1.2 seconds. What we really care about here is the delta t. Delta t in this case is 0.4 seconds. So just be aware that in these equations, we're using physics shorthand. It's not necessarily to your advantage, but that's what the AP Physics exam does, so that's what I'm going to do as well. All right.